Hi, everyone. My name is Devansh Jalota, and today I'll be presenting our work on markets for efficient public good allocation with social distancing. So this is joint work with Professor Marco Pavone from Stanford, Professor Chi Chi from Hong Kong University of Science and Technology, and Professor Yinyu Ye from Stanford as well. So to start off, what really is a public good? So a public good is one that is characterized by two main features. The first being that these goods can be consumed by people without reducing the availability of these goods to others. So take, for instance, the street lights that we have on our roads. The second major feature of public goods is that these are goods of which no particular person in society can be deprived. So, for instance, we have public parks wherein we have no particular monetary charge that is placed in order to use these parks, thereby making such public spaces very easily accessible. However, it is exactly this ease of access with regards to public goods that often leads to some of the issues with regards to the use of public goods. And in particular, it very often happens that public spaces tend to be far more overused, as in the example of this beach, as compared to what most of us would like when we're going out and using a public space such as a beach. And on the complete other end of the spectrum, we have with the COVID-19 pandemic that due to the strict social distancing restrictions that we need to meet, it very often has happened that public spaces have tended to be almost completely unused or very much underused, thereby generating very little value to society. And what both of these contrasting outcomes has suggested, and what has actually ended up happening due to the pandemic, has been that there have been certain capacity restrictions that have been imposed in the use of a myriad range of public spaces across the world. And this not only helps in making people more comfortable in terms of using public spaces, as in the pandemic, but it also helps in curbing these overuse concerns with regards to public goods. And so, to get to the major point of this work, the idea is that we would like to design certain mechanisms such that we can achieve an intermediate outcome between these opposing scenarios that I just presented. That is, we would ideally want to have beaches, for instance, that are neither too overused nor completely underused, and thus we're still generating a decent amount of value for society as a whole. So, in order to motivate how we might do this, we're going to specifically consider the design of market based mechanisms to try to achieve this middle ground. And in particular, what we observe is that due to the capacity restrictions that have been added by the pandemic, that we have a strict supply as far as the amounts of goods that we have available to us are concerned. However, in many public goods allocation problems, very often happens that the demand for these goods far exceeds the supply of these goods. And so, one of the goals of this work is to try to find that equilibrium price such that we can make supply meet demand. And as we develop sort of this equilibrium or the sweet spot within our economy, we would like to maintain certain nice properties of this particular equilibrium. And in particular, we would like to ensure that each person receives their most favorable bundle of goods under the prices that are set within the market. So, in order to develop our specific market mechanisms, we are going to leverage the theory of Fisher markets. And in particular, what Fisher markets tell us is that they solve a resource allocation problem when agents have, or people in our economy have budget constraints, and the goods in our market have capacity constraints. However, in many public goods allocation problems, there are certainly a range of other types of constraints, which we call in our work as physical constraints, that tend to come up. And these are not accounted for by the Fisher market framework. And so the goal of this work is to try to extend Fisher market theory to essentially solve a resource allocation problem, not just under budget and capacity constraints, but to also extend this to adding certain other physical constraints. For instance, knapsack-like constraints that may not have been considered by classical Fisher markets. So just to give you a taste of what some of the existing work some of the existing literature within the space of generalizing Fisher markets to different types of constraints, what we have is that most of these generalizations are limited to the spending constraints of buyers and the earning constraints of sellers. However, for instance, if we wanted to have a knapsack-like constraint, there haven't been any real generalizations of Fisher markets to such types of constraints. And the goal of this work will be to try to derive market clearing prices when we have these additional physical constraints within our model. So let's get right to modeling our problem then. So in particular, we're going to assume, as with Fisher markets, that each of the agents in our economy are utility maximizers. And so in particular, let's suppose we have an agent. Let's suppose we have M goods, in this case, 3 coffee shops in our economy. And this agent derives a linear utility from the consumption of these goods. So in particular, we're going to assume throughout the rest of this talk that the agent's utilities are linear in the allocations. And so in particular, if the agent derives a utility uij, which is the amount of utility they derive from consuming 1 unit of good j, and xij is the quantity of good j that they consume, then what we can do is that for this given agent, the total utility that the agent derives is summing over all of the goods of uij times xij. And the decision-making problem for this agent is very simple. That is, if the agent prefers to go to Starbucks the most as compared to the other 2 coffee shops, then under no further restrictions on this model, this agent is just trying to maximize utilities, and so will always end up going to a Starbucks as compared to the other 2 coffee shops. However, now what we observe is that the pandemic, in fact, adds these additional capacity restrictions within our particular framework. And in particular, what it does is that we're adding these additional capacities, S1 bar, S2 bar, S3 bar, for the 3 different coffee shops within our model, which were not there pre-pandemic. And so now the question is, what does this agent do in lieu of these new capacity restrictions that have been imposed? So in particular, what may happen is that this agent comes out in society, and this agent realizes, well, Starbucks is being used to capacity, and so, well, I can't really go to a Starbucks at the time I enter the market, and so I must settle for my second best option, which in this case is Costa Coffee. And so essentially what this suggests is that agents are no longer guaranteed their most preferred good. And the fact that one agent's decision-making problem is inherently coupled with the decisions of other agents, primarily because if somebody else chose to go to a Starbucks, that's affecting my ability to go to a Starbucks now. And this is primarily due to these capacity restrictions that we have imposed. So now what this suggests is that we need to transition from just looking at an individual agent's problem to actually looking at a more global or a societal scale problem. So in order to do that, let's suppose we have n agents or 6 different agents in this particular example, and we have the same goods with a capacity of 2 imposed on each of the goods. And now the question for us is, well, how do we partition these 6 agents amongst these 3 goods so that we can, let's say, get a socially desirable outcome? So in this case, to motivate what we might want to do, let's just suppose that all of these 6 agents have the highest utility for going to a Starbucks. So in this particular case, if we look at a pre-pandemic scenario, then all of these 6 agents would have very easily just gone to a Starbucks and thereby gotten the highest utility. However, now that we've imposed these capacity restrictions, what we observe is that we have a discrepancy between supply and demand, wherein we have a demand of 6, but we only have a supply of 2. And so in order to reconcile this discrepancy between supply and demand, what we ideally want to do would be to price these goods. So in particular, we would end up pricing Starbucks the most, Cafe Nero the least for these particular set of utilities. And we would obtain in that particular case that the market clears. However, one thing that you might think is, well, we're looking to price goods that are supposed to be public at the end of the day. And so wouldn't this defeat the purpose of the goods being public in the first place? And essentially the way we address this in our work is that we treat the prices in our market in the form of artificial currency. So essentially we're going to impose a price, P sub j, for good j within the market in terms of non-monetary units. So we're not going to have any monetary transactions taking place. And because our goods are being priced in artificial currency, we would like agents to be able to transact in this new currency. And as a result, we're going to endow agents with a certain budget, W sub I for agent I, that they can then spend in the market. So one way to think of what a fair endowment would be is that each agent in the economy is given exactly the same amount of budget. And thus, no matter what socioeconomic or racial background you're from, you will have exactly the same buying power as somebody who is far more wealthy than you, for instance. So with this, with sort of these additional constraints, with, for instance, us setting prices on goods and with these budgets, the question is, how does an individual's decision-making now change in response to this? So in particular, we've now imposed these prices, P1, P2, P3 for the 3 different goods in our market. And we've given this agent a certain budget. And now the question is, how does an agent's individual optimization problem change? So in particular, now the agent is still going to maximize the linear utilities, but now subject to a budget constraint. So essentially, the total amount of payments that they must make must not exceed the budget. And finally, there's just a simple non-negativity constraint just to ensure the feasibility of the resulting allocation. So essentially, this is what the agent's individual optimization problem will be the moment we impose capacity restrictions and agents have a certain amount of budget that they cannot exceed. So with this in place, one thing that is very natural to ask is, how do we set appropriate prices within the market such that our market clears? And essentially, this is where Fisher markets come into play, wherein they provide us with a social optimization problem or a centralized optimization problem, which enable us to set the appropriate market clearing prices within our economy. So in particular, what is the social optimization problem? This involves maximizing a social aggregation function, which is essentially, in this case, just sum over all agents of WI, which is the budgets, times the log utility. So we're just summing over all agents of their budget weighted log utilities. So that's our objective. And then as far as the constraints are concerned, we want the supply to equal to demand. So this is our capacity constraint within the model. And then we, of course, will have a non-negativity constraint to ensure the feasibility of the resulting allocations. So now, in order to set appropriate prices in the market, what Fisher markets tell us is that we should be setting prices based on the dual variables of our capacity constraints. And why are these the right prices to set within the market? Well, the Fisher market literature tells us that if we look at our individual optimization problem of maximizing utility subject to budget constraints and the social optimization problem, then in fact, we can show that both these problems are KKT equivalent. And in particular, what I mean by this is that if we set the prices in the market based on the dual variables of the capacity constraint, and we set those prices within our individual optimization problems, then in fact, what we're going to observe is that the optimal allocations corresponding to the social and the individual optimization problems will be exactly the same. And what this suggests is that not only are we maximizing a societal objective, but in the process, we're making sure that at these prices, each individual is as happy as they could potentially be under the prices that are set within the market. And as a result, Fisher markets provide us with a great framework of setting the appropriate market clearing prices within our economy. So now the question that we ask in our work is, how can we generalize this framework to the scenario when we also have these additional physical constraints and still be able to derive market clearing prices under these additional constraints? So let's first start by motivating what these additional constraints may look like. So let's just let T sub I be the physical constraints associated with the ith agent. And to illustrate what these constraints may look like, let's suppose that we have a set of parks, libraries, and coffee shops within our neighborhood. And let's say we have an agent who says, well, on a given day, I would like to go to one park, one library, and one coffee shop. And so essentially what this agent is doing is that he's imposing a very strict physical constraint in terms of the types of goods that this person would like to avail within the market. And in a pre-pandemic environment, this agent would have just gone to the best park, best library, and best coffee shop. But certainly, this agent can no longer do that the moment we've imposed these additional capacity restrictions on our goods due to the pandemic. And so let's just try to think of, if we applied the Fisher market framework to this setting, when an agent is imposing these strict physical constraints, what Fisher markets as a black box would end up doing in this case. So in particular, we have this scenario wherein we can, just for illustration purposes, suppose that this agent has really high utilities for coffee shops as compared to the other two, the libraries or parks. So in this case, what Fisher markets may tell us is that, well, this agent has a really high utility for coffee shops, so I'm just going to send this agent or allocate this agent to 3 coffee shops rather than allocating this agent to one of each of the 3 different goods. And essentially what this suggests to us is that Fisher markets, because they're not explicitly accounting for these physical constraints, that they may give us highly undesirable allocations at the end of the day. And Thus, the most natural thing for us to do in this context is to actually try to extend the Fisher market framework to explicitly accounting for these physical constraints so that we can avoid such undesirable scenarios from occurring. So let's do exactly this. So in particular, we're going to consider a new individual optimization problem, which I'm going to call IOP. And in particular, we're going to still be solving, each agent is still going to be solving a utility maximization problem in this particular context, subject to a budget constraint as earlier. But now we're going to add in these additional physical constraints given by a matrix A. And then we're going to just have these constraints be linear. So AX less than equal to B for some vector B. And certainly we're going to still maintain non-negativity. So essentially all that we've changed from our classical Fisher market problem is that we've just added these additional physical constraints and kept the rest of the problem with the budgets and the utility, the objective exactly the same as earlier. And so now the most natural thing for us to do, as we did with classical Fisher markets, is to ask, well, how do we set prices within this new market where agents also have these additional physical constraints? However, before we get to that question, a more immediate question to ask is, does this price even exist and is it unique? And in the case of classical linear Fisher markets, such a price is guaranteed to exist and is guaranteed to be unique. However, we can show by constructing some simple examples of markets wherein the market equilibrium, in fact, may not exist in the addition of these physical constraints. And furthermore, it may not even be unique. And to add on to both these negative results, what we can also show is that with classical linear Fisher markets, certainly people purchase goods corresponding to the maximum bang per buck ratios of each of the goods. However, in this particular case, it is not too hard to see that because of the addition of the physical constraints, people will no longer be able to purchase goods corresponding to the maximum bang per buck ratios of the goods. And essentially, what this suggests to us is that we can't shoot as high as trying to generalize our problem or to be able to set market clearing prices for all types of physical constraints, but we might need to impose certain assumptions to be able to overcome the barrier of existence so that then we can go on to actually derive market clearing prices within our economy. So in order to do that, the specific, our first major result is to actually establish a condition to guarantee the existence of a market equilibrium. And in particular, the condition that we require is that there should be at least one good within our market that does not belong to any particular physical constraint. And this is in fact a really mild assumption because one can consider a suite of markets wherein there will certainly be goods that do not need to be tied to physical constraints. For instance, real money could be an example of such a good. And as a result, the only real condition that we need is that there is a good that does not belong to any physical constraint. And the basic idea behind the necessity of this condition is that if we have such a good that does not belong to any physical constraint, then this enables an agent to buy any amount of that particular good and thus be able to spend their entire budgets, which they otherwise would not have been able to do due to the physical constraints. So we've been able to resolve the question of existence. However, the question of uniqueness or trying to resolve it in some way still remains. And however, what we've been able to show is that even though people do not purchase products corresponding to their maximum bang per buck ratios, they in fact purchase goods in the descending order of the so-called virtual products as bang per buck ratios. And so essentially in our work, we define the notion of a virtual product and show that this particular claim is in fact true. But what we can observe is that the problem of solving Fisher markets with physical constraints seems to be fundamentally different through some of these results as compared to classical linear Fisher markets. And thus, it also makes this problem far more interesting in terms of deriving prices. So now the next question for us is, how can we actually derive the appropriate market clearing prices within our economy? And so in order to do this, we're going to try to leverage a similar idea as with the social optimization problem with classical Fisher markets. So in particular, we're going to consider the same IOP, and now we're going to consider a new social optimization problem called SOP-I, which is going to be exactly the same social optimization problem as classical linear Fisher markets, but all we're going to do is we're going to add these additional physical constraints. So the primary reason for doing this is that we would like our resulting allocations to satisfy these additional physical constraints that we've added. And now the question for us is that are these two problems KKT equivalent? That is, if we set prices corresponding to the dual variables of our capacity constraint, then are the optimal allocations of both of these problems the same? And in fact, what we can show is that this is actually not going to be the case. And in fact, it is really only going to be the case if we have that all of our physical constraints are homogeneous, which is to say that our BIT values that we have on the right-hand side of our physical constraints, they're all equal to 0. But in the more general case, we can show that by deriving the KKT conditions of these two problems, that in fact, these two problems are not KKT equivalent, and thus we cannot set equilibrium prices using this particular social optimization problem. And as a result, what this suggests is that we need to do something a little different. And in order to motivate what we might want to do, let's just consider our SOP-I problem that I just defined. So in this particular case, what are we really doing? So we're basically saying that for each agent within our economy, we're going to weight the agent based on their budget endowment that they have. However, so this sort of and this budget endowment serves as, in some sense, a priority for this agent within this market. However, this seemed like the right thing to do with classical linear Fisher markets. But the moment we've added these physical constraints, what we show in our work is that just prioritizing agents based on their budgets is insufficient. And in fact, what we need to do is we need to add so-called budget perturbations, which leads to the definition of this new problem, which we call BP-SOP, or the budget perturbed social optimization problem. And essentially, all that we do that's different from SOP-I is that we add budget perturbations in the objective and leave our constraints exactly the same as with SOP-I. So that's the only change that we've done here. And just to give you a bit more of an intuitive feel of what these lambda I perturbations are doing here, let's consider the following scenario. So we have one agent who has very few physical constraints. And so this gives him a lot of slack in terms of the type of goods that this person can avail within the market. Whereas let's say we have a medical care worker who is highly constrained and or highly physically constrained, and so has, for instance, very little time available to actually make use of the public goods within the market. And as a result, if this particular agent is not guaranteed to get goods within their restricted feasible set, then this agent certainly cannot spend their entire budgets, which essentially prevents the market from clearing. So what we would need to do in this context is we need to give a low prioritization to a less constrained agent and give a higher prioritization to a more constrained agent, so that we can guarantee this more constrained agent gets a good within their small feasible set. So in particular, to understand what values these lambda i's should take within our market, we have the following main result of our work, which essentially states that let's consider this IOP and let's consider our budget perturbed social optimization problem. Then in fact, what we can show is that these two problems are KKT equivalent under a certain condition on the lambda I variables that we have here. And in particular, if RIT is the dual variable of our physical constraint, then if our lambda i's take on a value equal to sum over all the physical constraints of RIT, BIT, then if we set prices based on the dual variables of BP-SOP's capacity constraints, and we set these prices within our individual optimization problem, what we observe is that the optimal allocations of both of these problems are exactly the same. And essentially what this suggests to us is exactly what it suggested to us with classical linear Fisher markets, which was that we are solving a societal objective. And in the process, we've obtained the appropriate market equilibrium prices such that each agent is potentially as happy as they could be under the prices that are set. So essentially what we've been able to do here is we've been able to generalize Fisher markets to now accounting for these additional linear constraints given this particular condition on our budget perturbations. Now, one thing that you might think is, well, this lambda I that we have, the budget perturbation, is implicitly defined in terms of the dual variables of our physical constraints. And so the question is, how do we actually compute this problem given that we do not know this value of lambda I a priori. And so in order to do this, what we do is we propose a fixed point iterative procedure. And in particular, just to give you a taste of what this fixed point procedure looks like, we say, let's initialize lambda to some value, let's say the vector of all zeros. And then we're going to solve our budget perturbed social optimization problem and extract the dual variables from there. And then we're going to reinitialize the lambdas, again, solve the budget perturbed problem and keep iterating until we converge. And numerically, we've gotten really good and fast convergence guarantees. However, trying to show this theoretically still remains an open question. And so finally, just to wrap up, what we've been able to do within this work is to design a market mechanism that derives market clearing prices while supporting additional constraints. And in particular, we've set prices to clear the market. And we've been able to make sure that while maximizing societal objective, each person is as happy as they could be under the prices that are set within the economy. And just to give you a taste of some of the future work, so on the theoretical side, certainly characterizing the convergence of the fixed point scheme, I think is a really important problem. And whether it's even possible to characterize the convergence in terms of the fact that is this problem actually PPAD hard in terms of this fixed point iterative scheme, then can we generalize this work to also having integral allocations? Because in the real world, we would like to make integral or discrete allocations rather than fractional ones. And what is the social efficiency loss when we make these integral allocations? And finally, what happens when customers arrive into our system sequentially? Can we still generalize this framework in that context? And then on the applied front, can we do certain pilot studies with industry? And this is some ongoing work of ours wherein we're trying to derive market clearing prices when we do not have access to agents' utilities in the presence of these physical constraints. And essentially, one way to do that is to learn consumer behavior using real world data. And finally, what are some regulation and enforcement challenges that come when we're trying to apply this problem, especially in the public goods allocation context? So I'll leave this concluding slide with my email and a link to the archive paper. And I look forward to any questions that you may have. And thank you so much for listening.